Okay, so the most basic equation is a linear equation. So linear function is going to be a line, which means it's going to be x to the first power. Obviously, it can be in that form of y equals mx plus b, or it can be in the form of point slope form. The graph may have different y-intercepts. It may have a different slope. Could be a positive, could be a negative slope. But in this case, this linear function, this is the parent graph y equals x, has a y-intercept of 0, has a slope of 1 because the m is that hidden 1 in front of the x. And then your domain and range is all real numbers. In this case, the end behavior is as we approach negative infinity, that means as we follow the left arrow is going down. So it's going down to negative infinity. And the right arrow, the arrow on the right, that's x approaching positive infinity. Here, my y value is approaching positive infinity. It's going up to positive infinity. Next up, quadratic function. We're going to see this a lot as well. Y equals x squared. In this case, for this parent graph, the domain is all real numbers. Those arrows are going to continually move further left and further right. But the range is not going to be all real numbers. The range is going to start at a y value of 0, and it's going to rise up to positive infinity. Okay, so the end behavior for this particular parent graph is as we follow the left arrow is going up. As we follow the arrow on the right, that right arrow is also going up. Okay, next up, cubic function. Cubic function y equals x cubed. It's always going to have that that S shape or something related, either that S or that reflected S shape. And and the easy way to find order pairs for y equals x cubed, you can just plug in order pairs around 0. So if I plug 0 in, I'll get 0, 0. If I plug -1 in, I'll get -1. If I plug 1 in, I'll get 1. And then those 3 points there kind of helps you guide your graph here. No, it's not going to be quite a linear graph, even though it's lined up -1, 1, 0, 0, and 1, 1. It's going to be a curve. So it's going to have that kind of S shape about it. Domain and range, all real numbers, and end behavior for this parent graph. As we follow the left arrow is going down. As we follow the right arrow is going up. Okay. Reciprocal functions, these are rational functions, very similar to what we worked on yesterday. This is the parent graph 1 over x. Now, 1 over x has a vertical asymptote of 0, right? We talked about how any x in the denominator that doesn't go away is a candidate for your vertical asymptote. So if I set that equal to 0, x equals 0, there's my vertical asymptote. And if I want to find my horizontal asymptote, I compare degrees, right? So numerator degree is 0. Degree in the denominator is degree 1. Degree 1 has a higher degree than the numerator. In that case, my horizontal asymptote is always going to be 0. So I have 2 asymptotes along the axis, both axes. And if I choose points on either side, if I plug 1 in, I'll get order pair 1, 1. If I plug -1 in, I'll get -1, -1. And as long as we know some target points, we know how the graph's going to look, right? Because we know our graph is going to kind of curve towards the asymptotes, and it's going to always have that shape in the sense that it's going to kind of move towards the asymptotes as we move away from the origin. Okay. The domain is all real numbers except 0. The range is also all real numbers except a y value of 0. So we work around those restrictions. So that's why we have, that's how it looks in interval notation. Okay. As we approach negative infinity, as we follow the left arrow, the left arrow is headed towards a y value of 0. As we follow the arrow on the right is headed towards also a y value of 0. So the end behavior, they're both headed towards the that horizontal asymptote of y equals 0. Okay, next page. So we're going through the basics. These are very useful and functions that we see a lot. Okay. Hey, these are ones that you may be less familiar with, but these are also important. Okay, so next up is the square root function. Square root function kind of looks like a sideways parabola with only one half of it showing. Right. The y equals square root of x. You can get a quick feel for this graph just by plugging in order pairs 0, 0, 1, 1, 4, 2. So it's moving faster to the right than it is going up. So it is a pretty slow moving graph. It is rising, but it's rising at a not as fast of a rate as, let's say, a quadratic function or y equals x squared. Okay. So your parent graph of y equals square root of x, it starts at 0, 0. So that's why the domain and range, they both start at 0. Okay, so from 0, we're going to go to the right to positive infinity. And for range, we also start at a y value of 0, and we go up to positive infinity. And behavior, as we follow the right arrow, as x approaches 0, that means here, if we're approaching 0, the y value is approaching 0. So it looks like it's not, the end behavior doesn't extend past that y-axis. And the reason why is because if I were to insert like -1, -2, I'll get a square root of a negative number, right? We know that a negative number cannot exist inside a square root, at least not in the real number system. So that's why the graph starts here at 0, and it's only in the positive values after 0. Okay. As we follow the arrow on the right arrow is also headed to positive infinity. It's going up to positive infinity. Okay. Cube root function kind of looks like a cubic function. It's just the s is more sideways than vertical. Okay. So you can always, if you're unsure what that graph looks like, you can kind of get an idea just by plugging the order pairs: -1, -1, 0, 0, 1, 1. However, rather than rising up like this, it's going to kind of rise. It's going to kind of a little bit flatter, a little bit more linear in the sense that it's going from side to side instead of going from bottom to top. Now, it is still rising and falling. It's just rising and falling at a very, very slow rate. Okay. Domain and range, all real numbers. Follow the left arrow, it's going down to infinity. Follow the right arrow, it's going to positive infinity. It's going to go up to positive infinity. Okay, so on this second page, these next two are the most important for what we're going to see. Okay, exponential and log and natural log. Okay, so it's important that we really kind of have just a quick idea as to how the graph is going to look. So exponential function y equals e to the x, it grows at a very fast rate. So e to the x, base e is a base that we're going to use a lot. So e to the x, e is around like 2.7. So 2.7 to the first power, 2.7 to the second power is going to rise very, very quickly. But there is a horizontal asymptote. So the graph is not going to dip below the y-axis, sorry, the x-axis. So my domain is all real numbers. The arrows are going in both directions, but the range is only in the positive region. It's only going to go from 0 to positive.
How do you, like, is the horizontal axis is always going to be like 0 unless otherwise like noted?
Yes. For the parent function, it will be 0. But if there's transformations that we're going to discover later in this course, I'm sorry, today, the transformations you'll be able to see where that transformation is going to produce a different horizontal asymptote. But just know that for every exponential function, there will be an asymptote. You just have to be able to know where to find it. But you know where you know to look for it. Yeah, and it's helpful because having that asymptote there kind of shapes your graph, right? You know that your graph is going to flatten out on one end towards that asymptote. Okay, next natural log function is log base e. Natural log of x and log base e. This is the inverse function of the exponential function e to the x. So what that means is if I were to fold this graph over the line y equals x, okay, so imagine there's a y equals x line over here. If I were to fold the graph over that diagonal line, I'm going to end up with a natural log of x. Okay, so it's the inverse function. We'll talk a little bit more about inverse functions. But basically, your x and y variables are swapped. So every order pair here, if I flip that order pair, I'm going to get an order pair on this graph. Okay. So because of that flipped relationship, rather than a horizontal asymptote, your natural log graph is going to have a vertical asymptote. And rather than simply being above the x-axis, a natural log graph is going to be to the right of the y-axis. And then you can also see a nice relationship here. Your domain and range, it's going to be flip-flopped on the natural log graph, right? So the domain is the range of the exponential. The range of the log is the domain of the exponential.
How do you know for the logarithm function, like when it starts to like curve as you're ascending?
Right now, you don't have to worry too much. You just know that it is rising at a pretty slow rate. It's not like an exponential graph where it's shooting up. So just know that your natural log graph and your square root graph just has a slow growth about it, but it's just make it curved. We don't have to know specific order pairs. Maybe in some instances, but for the most part, as long as right now, I just want us to know, if I say it's a natural log graph or exponential graph, I want you to be able to just have a visual. You have an idea how the graph is going to look, and then and that's going to be useful when we're having to sketch a graph without the use of a calculator. But okay, any questions so far? Absolute value function, we're going to see this a bit as well. Absolute value function looks like a V, either a V that's right side up or a V that's upside down. Okay. So I can just, if I use my order pairs here, if I just plug values around 0, I can quickly get the picture of this graph. If I put -1 into this notation, that -1 is going to cause the output to become positive. So -1 has a y value of 1. 0 is still 0. If I plug in 1, 1 is already positive, so it'll stay as 1. So if I have -1, 0, 0, and 1, 1, those 3 points already form like a small V. If you just connect those dots, you can see it's going to be V-shaped graph. And as a side note, I think this will be useful as well. Let me just go ahead and include this as well. Well, first off, domain is all real numbers. Your range is going from 0 to positive infinity. Now, absolute value function, a lot of times it's a little bit cumbersome from a calculus perspective to work with this function in terms of derivative that we're going to see down the line. So sometimes we like to rewrite this as linear equations. Do you see how this graph is basically, you can think of it as 2 linear graphs that is stopping at 0, 0. So sometimes we like to transform or rewrite this absolute value function as 2 linear graphs, and we call that a piecewise function. So let me write it this way too. We can also write it as y is equal to, you have y equals x, that's going to be this linear graph because that's a positive slope. And then we also have y equals -x, and that is this linear graph. However, we're not extending the graph all the way through, right? Because if we did, then it would look like an x. And if it looked like an x, it would no longer be a function because it wouldn't pass a vertical line test. So the way that we can limit these lines so that it actually forms that V is if we say that, okay, I only want this positive slope to show to the right of 0. And for negative x, I only want this negative slope to show to the left of x. Sorry, left of 0. Now, 0, 0 is defined. It doesn't matter which one you define it. You can define it either with this positive slope graph or this negative slope graph. But we just want to make sure that we have an equal sign with either one of these. They do meet at the same point. So we choose either one, and either one is sufficient to form that last point where they meet. Okay. So if I were to graph this, this would be the same as absolute value function. But again, the advantage is working with polynomials. Linear is a little bit cleaner and easier than absolute value function. We'll discover that later, but right now I just want to make that connection between absolute value function and linear functions.
So piecewise functions like usually be associated with absolute value?
Or
does it just depend?
It depends. It depends. Okay. But right now, just know that your absolute value function can be written as a piecewise function, as the combination of two lines connected together. Okay. All right. So now that we have those parent graphs introduced, let's talk about how we can move those paragraphs around using transformations. So have you guys copy this down here. So transformations of parent graphs. Okay, so given a parent graph, right, either like y equals square root of x or y equals cube root of x, any of the parent graphs that we saw on the previous pages, we can always do these various changes to it. And the nice thing about understanding these transformations is it allows us to get a quick view of the graph without having to painstakingly, plug in every order pair and use a table of values, right? If you have an idea how the original graph is looking, and if you have a basic idea as to what these transformations are doing to it, you can get a quick sketch of the graph in a matter of seconds rather than spending minutes trying to build the graph. Right. Okay, so here are the list of transformations that we're going to be. There's more than these, but these are the ones that we're going to be responsible for. First, there's the negative. Okay, that's one thing. That is different than the A. So the A is going to do the job of stretching or compressing your graph. The H and K is going to do the job of either shifting the graph left or right from your original parent graph position. Okay, so let's start off with f of x plus h. So this h here, whatever number you see in here, is going to shift left or shift right, but just understand that it's going to go in the opposite direction of what you would expect. Okay, so if you see a +3 or +4, that's going to shift your parent graph to the left. Okay, if you see a -4 or -6 or -8, that's going to shift your parent graph to the right. Now, any number that is outside, I'm going to call it +k. That's more straightforward. Okay, as long as you understand that's a vertical motion, it's going to be straightforward in the sense that positive k is going to shift it up that number of units. Negative k is going to shift that graph down those number of units. Now, the number in front that's being multiplied to your function, that's going to be a vertical stretch or a compress. So if it's like a number like 3 or 4 or 6, that's going to shift the graph, or that's going to enlarge the graph vertically by that factor. But if it's like 2/3 or 1/3 or 2/5, those are all numbers less than 1. We're going to have to. We know it's going to be kind of pressing the graph down. It's going to be a vertical compress. Now, I want us to understand that if we see a -5 or -6, -5 and -6 is still a vertical stretch, even though in our minds we're thinking that it's less than 1, because the negative is not doing the job of stretching it. That negative is simply reflecting. Okay, so we have to understand that we really want to separate a negative from this number. Okay, so if I see a -6, don't think of, oh, -6 is less than 1, so that's compressed. It's negative being the reflection and the 6 being a stretch. Okay, so let's do a few of these here. For the following function, let's identify the parent graph, list the transformations, and we'll find the domain and range, and then we'll also sketch the graph. So look at this function here. What is the parent graph that we're working with to begin with?
Okay.
Yep, y equals x squared, right? So y equals x squared normally starts at 0, 0, right? We know what the basic graph looks like. So we know it's going to move that parent graph because of that 3 and that 1. And the nice thing here is that this, you can think of this as the ordered pair of your center, of your vertex. Okay, so basically, if we can move the center of the graph, then everything else kind of falls into place. So here, the vertex, again, we have to understand that we're going the opposite direction of what we see in here. So instead of -3, we want to think of it as moving to the right 3 units. So the vertex is just going to be 3, 1. Okay, so it's going to move that center from 0, 0 all the way over to 3, 1. And if I can get that center figured out, then I know my graph is going to form in that shape. Okay, and now the next thing is, what is that 2 going to do to it? It's going to stretch it, right? So a quick way to do this is normally a parabola is going to, at least for the first points, it's going to go up 1 over 1, up 1 over 1. But that 2 is going to basically think about it as a slope. It's going to go up 2 over 1, up 2 over 1. It's not going to follow that pattern all the way through, but having those 3 points is helpful. It kind of helps you kind of begin forming your graph. And that's all we need. We just want a very basic sketch of the graph. We don't have to be super accurate in terms of knowing every order pair. When we get to area and volume in the second semester, if we can just get a basic sketch of the graph, that's enough for us to get our bearings, and then we can make the calculator do the work for us. Right? But a lot of times, we want to be able to just set a problem up, and we don't want to be completely lost looking at a function and not knowing, what the shape is or where it could be.
So why would it be like up 2 over 2 instead of like up 2?
Because up 2 over 2 is same thing as up 1 over 1. Right. That 2 is going to rise faster than it's moving to the right. So that's why it's going to feel like it's getting pulled. Thank you.
Thank you.
Okay, so let's list out our domain and range. Our domain and range is, domain is going to stay the same as the parent graph, but the range is going to change a little bit because we're going to start at 1 because the graph did shift to the right, shift up 1 unit. So start at 1 and go up to positive infinity. Ultimately, guys, it's not going to be that important for us to be accurate in our graph. It's more important for us to just be able to identify, what's happening. If you can verbalize what's happening to the graph, then it's okay. As long as you can identify the basics of the graph, that's more important than, oh, am I getting my order pair right or wrong? That's really not that important. In terms of what we need to do, because if it needs to be super accurate, then the College Board will give us, it'll be part of a calculator section that we can use. But right now, I just wanted to just kind of, so that we're not completely lost looking at a graph and knowing, what's happening to it. Okay, so number 2, see if you can identify your parent graph, right? Visualize your parent graph, identify what's happening to your graph, identify the transformations, and then let's see if we can do a quick sketch of this graph. Can someone say what the three transformations that's occurring here?
It's x-axis reflection.
Okay.
Shift up by 1, shift left by 3.
Good. So that's that -3, 1 is also very helpful in the sense that we know square root of x starts at 0, 0. So that -3, 1 is basically the starting point of your radical function as well. Okay. So here's what your graph will look like. So instead of starting at 0, 0, just think of it as, okay, it's not my vertex of a parabola, but just think of it as, oh, I'm shifting my graph from 0, 0, left 3 units and up 1, and that is my starting point. Normally my starting point for my radical function is 0, 0, but I'm just going left 3, up 1, and it's reflected. So rather than rising up, it's going to be going down. So it's basically showing me the other half of the parabola instead of the upper half, because that reflection. Yes.
Does this one ever go like the other way, like curve like to the left? Or is it always gonna?
Yeah, it could curve to the left if there is a negative inside, if the x is negative, but I don't think we're going to see that too often. Yeah, but if the x is positive, it's gonna move to the right. Yeah. But yes, it could open to the left if the x is negative. Okay, try number 3. See if you can sketch your graph based off of the transformations that you see. So number 3 is similar to number 1 in the sense that your absolute value function has a vertex just like a parabola does. So what is the vertex of this, or the center of this absolute value function? -4, -1. So if I can find the center of this graph, it's easy. I can just create a V out of it. Notice that there is no stretch. So it's just going to be a slope of 1. So it's going to be up 1 over 1, and it's just going to be a V-shaped graph there.
It's kind of like the quadratic function where it's like up 1 over 1, like
Yeah. Mhm. All right, next page, page 8, number 4. Okay, so this one is a rational function, right? So a rational function looks like this. At least the parent one looks like this. But here, I think it's easiest to understand, okay, rather than finding a starting point for my graph, if I can just know where my asymptotes are. So I'm just going to shift my asymptote where they need to be, and then I can just kind of sketch my graph around those asymptotes. Okay, so, but let's just go ahead and identify those transformations here. Normally, my function is 1 over x. So what's happening to it? 2, okay. Mm-hmm.
and down 3.
Down 3. So basically, that is also that left one down 3. Think of it as, oh, I'm just moving my asymptotes in those directions, right? So rather than, so my vertical asymptote was at 0, I'm going to shift that asymptote to the left, which is x equals -1. My horizontal asymptote was at 0, but I'm going to shift that asymptote down 3 units. So if I can just have my asymptotes in the right place, then sketching the graph is just, we don't have to worry about any order pairs at all. We just sketch the graph. And in terms of the stretch, we understand it's a stretch, but you know, we can just do our best estimation with our graph. It's not that important in terms of accuracy. It's more important that you just understand where it is, what's happening to it, but don't worry so much about, oh, wait, am I getting my order pairs right? Because even if you, for some reason, get the stretch graph portion wrong, you're still able to identify the domain and range with perfect accuracy, right? That stretch is not influencing your domain and range if you get the asymptotes right.
Why is the parentheses for like -1, -3 for domain and range? Because it like stops. Okay. So
Because of the asymptotes, right? It can never reach those points, right? Okay. Let's look at number 5. E to the x plus 2 minus 3. Let's just sketch what we know about the parent graph. Y equals e to the x is always going to have an order pair of 0, 1. Anything that is raised to the 0 power is going to be 1. So as long as I know that is kind of like my anchor point, I can kind of just work around it. And I know that is my parent graph, right? That is what I'm starting with.
it's like 1, 1. Oh,
0, 1.
0, 1.
Yeah, 0, 1. Yeah. All right. So what transformations do you see here? Left 2, down 3. And that down 3, basically just think of it as I'm just moving that horizontal slope down, right? If I move that horizontal slope down, I can just work my graph around it. And then that left 2, okay, I can just make my point, my starting point also do that as well. I can make my starting point go left 2 and down 3. If I have that point at the asymptote, then sketching that graph is going to be pretty quick and easy. Okay, so I'm taking that order pair 0, 1, and I'm just going left 2, down 3. I know my horizontal asymptote is going to be at y equals -3. As long as I have that starting point and the asymptote, I can do a pretty good sketch of the graph because I know my basic shape.
So like different like the exponents, those are gonna be always opposite, like the constants since it applies.
That's right. That's right. Yeah. So think of that x plus 2 as opposite as well. So anything that is involving that is connected to the x, either in parentheses or and in the exponent, that is opposite as well, right? So that plus 2 is also shifting that parent graph to the left. The number that is sitting outside by itself, that's always the vertical motion, vertical movement.
How'd you get to the vertex again? 'Cause-
Oh, yeah, so we don't have a vertex. What we do have is a starting point. We know that y equals e to the x is going to have an order pair of 0, 1. And the reason why is if I just do a quick table of values, if I were to insert 0 into my parent graph, e to the 0 is 1. So that's my starting point. So if I can label that point, then I just know that I can just move that point 2 units left, 3 units down, and then that will be my anchor point for my
Yeah.
graph. Okay, number 6, natural log of x. Okay, that's my parent graph. So let me do a quick recap of natural log graph. Natural log graph has a vertical asymptote. And the anchor point is going to be at 1, 0. Okay. Now, I want to draw the connection here. If we know exponential and log and natural log, they're inverses of each other. So because there's an order pair of 0, 1, there must be an order pair of 1, 0, right? Inverse functions, your order pairs will always be flip-flop. So if I can have this as my anchor point, and if I know the shape of my graph, I know that is my parent graph. That is my natural log graph. So what is this x minus 3 plus 2 going to do? Yeah, so if I can shift my asymptote 3 units, and I just move that starting point up 2 units. So what I like to do is I like to just start off with my asymptote at 3. Okay. And then my quote unquote 1, 0 is going to be 4, 0, and I'm just going to move it up 2 units. If I have that as my anchor point, I just have to make my graph match the shape of my parent graph. Okay, so I want us to be able to see if we can start the next day's notes. So, being able to recognize graphs, that's important. But what's even more important is really having a firm concept or a firm grasp of trig, exponential, and log properties. Okay, because those are going to be kind of like the found. Now we're not going to dig into trig, exponential, and logs for another month or so, but we don't want to rehash all of the review. I want us to see if we can have the review up front, and that way we can just jump right into it. So the next thing I want to make sure that we can do is unit circle. Okay, so unit circle is going to be key. We don't want to have to feel like we're having to learn it from scratch. I want us to be able to review now so we can jump right into it. So let's do the review here. Unit circle, the most important thing is the first quadrant, right? If I can get the ratios of sine and cosine in the first quadrant, everything else falls into place very easily. Okay, so let's identify some important points here. So I'm going to highlight these points here. Okay. And we're not dealing a whole lot with degrees in this course. A lot of it's going to be mostly radians, but we understand that this is 30 degrees, 45, 60, 90, and it's just going to keep adding its way around that unit circle in intervals of 30, 45, or 60. Okay, so unit circle means that my radius to the circle is always going to be 1 unit. So my quadrant angle order pairs will be easy. That's just going to be 1, 0, 0, 1. And understand that all of your x and y variables are going to represent, x is going to represent your cosine, and y is going to represent your sine. So pi over 3 and pi over 4 and pi over 6. Here, let me I want to give myself more room here. I realize that Should have put this up here. Cosine of theta is my x, sine of theta is my y. Okay, so this is the way that I remember them. And there's multiple ways that students do it. I know that every one of my trig ratios has a 2 in the denominator. So I'm going to start at the upper left corner, and I'm just going to count starting with 1. So 1, 2, 3, and then back up that 1, 2, 3. Put square roots over all the numerator except for the 1, because I know square root of 1 is just 1. So I can quickly identify sine and cosine of each of these radian measures, right? Cosine of pi over 3 is 1/2. Sine of pi over 4 is root 2 over 2. Cosine of pi over 6 is root 3 over 2. Couple more important things here is that this acronym here helps us identify what are the signs of my trig functions. First quadrant, all my order pairs are positive x, positive y. Anything in the second quadrant has an order pair of negative x, positive y. And that S indicates that only sine is going to be positive here. Everything else is, well, sine and its reciprocal. So sine and cosecant are positive. Everything else is going to be negative. Right. Anything in the third quadrant has an order pair that's negative, negative. And that T represents only tangent is positive, or tangent and cotangent. Everything else is negative. Sine, cosecant, secant. Okay. And then the C in the fourth quadrant, order pair is all going to be positive followed by negative. Only cosine is positive, or cosine and secant are positive. Everything else is negative.
So in the third quadrant, only tangents. Also?
Oh, tangent and cotangent.
So tangent.
Right.
It's like the inverse or
Right, right, or reciprocals. Yeah, it's reciprocal and its function are positives. Another helpful thing to know is that tangent is same thing as sine over cosine, or in other words, tangent is simply y over x. So if I want to find the tangent of any of these first quadrant values, I can just do y over x. But these fractions may be confusing, so we can just cover up the denominator and say, okay, if I want to do cosine of pi, sorry, if I want to do tangent of pi over 4, I can just cover up the denominator and say root 2 over root 2. Okay, that's just equal to 1. Right? If I want to do tangent of pi over 3, I can do y over x, so root 3 over 1, which is root 3. So when we get the trig units, we need to be able to have this down, unit circle down. I'm not going to give you a blank unit circle because you're not going to be given a blank unit circle on the AP exam. So we do need to, be able to create our. I would say you only need to create the first quadrant, and then anything in the second, third quadrant, second, third, and fourth quadrant, you should be able to quickly gather. Okay. So, but for now, let's see. Yeah, let's see how much we can do in terms of filling out the unit circle. So let's just find all the radian measures first. Okay, if we can't finish it today, we can finish it tomorrow. So okay, so what I remember about the radian measures here is that everything that is closest to the x-axis will all share the same denominator. Anything that is in the middle will share the same denominator. Anything that is furthest away from the x-axis will also share same denominators. So basically, everything that's highlighted in orange will all have a denominator of 6. Anything that's highlighted in green will all have a denominator of 3. So the The relationship here is that you know it's going to be 3, 4, and 6, and then all the numerator is going to be one integer less than the denominator. So this is going to be 2 pi over 3, 3 pi over 4, 5 pi over 6. The nice thing about the third quadrant is that all your numerator is going to be 1 unit higher than your denominator. So 7 pi over 6, 5 pi over 4, 4 pi over 3. And in the fourth quadrant, it's going to be double the denominator minus 1. So 3 times 2 is 6. 6 minus 1 is 5. 4 times 2 is 8. 8 minus 1 is 7. 6 times 2 is 12. 12 minus 1 is 11. Okay, there's a lot of different ways, a lot of different tricks that people have shared in terms of memorizing the unit circle. But I think this is just, I want to make sure that at least we get the radians down. Okay, and then you know that every ordered pair is going to match exactly as the ones. The 3s will have the same order pair. The 4s are the same order pairs. The 6 will have the same order pairs. The only thing different is that you just have to match the correct signs for each quadrant, right? So second quadrant, all my order pairs will have an x value that's negative. In the third quadrant, all my order pairs will have negative order pairs. And then in the fourth quadrant, all my y values will have negative. So really, if you have the first quadrant, and if you know the radian measures of all this, there's no need to have to fill out the entire unit circle. Really, the first quadrant that you need, right? Everything else, as long as you know where cosine and sine refers to how to get to the tangent, you shouldn't have to create a full unit circle every time you're trying to work on unit circle values. Okay, so we'll continue to do some trig tomorrow. But if you have time, see if you're able to start working through this packet, because all this will be due on Monday. But we'll finish trig tomorrow and then also work on exponential and logs. Okay, come and get your phones.
Thank you. That's great.
Go ahead.
Here.
Yeah, 6.